Well, good morning, everyone. My name is Macarena García, and I'm here to present the work titled Tungsten Carbide Materials that sorry, microphone. So, just to have a slightly more dynamic presentation for all of us, I decided to divide it in 7 different parts, starting with a brief introduction of the topic. So, first of all, cemented carbides, also known as hard materials, have been widely used over the last few decades, and they consist basically of 2 different phases, a hard ceramic phase and a softer metallic binder. The most traditionally used cemented carbides have been Vidrios, from their name in German, and they are basically formed by these 2 phases, which are tungsten carbide ceramic phase and a cobalt metallic binder. The problem, as Alvaro has mentioned before, of cobalt is the highly reported toxicity. So actually, we are immersed of the search of tungsten carbide-based materials with similar mechanical properties, such as high hardness, high wear resistance, or high toughness. And that's why some other transition metals have been proposed for that reason. So, traditionally, cemented carbides applications have been linked to cutting tools, mining, or abrasion resistance, but due to their good mechanical performance under extreme conditions, they can be good candidates for high temperature applications. These kind of materials have been traditionally processed by dry techniques, but what we propose here is the colloidal processing of our materials, which basically consists of the addition, in our case, of ceramic or metallic powders to prepare suspensions. And actually, to just achieve a better dispersion of our particles in suspensions, we just use sometimes dispersants. The main advantages of colloidal processing are these 3, which are a high homogeneity of the mixture that we can achieve, the use of water as an eco-friendly solvent instead of any other organic solvents, and since we use suspensions, we work with suspensions, we can achieve actually really complex shapes on our final material. Traditionally, tungsten carbide materials have been sintered by really extreme conditions, under really extreme conditions, and actually the results weren't that good in terms of density or porosity. So the solution in this case would be the addition of a metallic binder. In this case, in our project, we decided to use a 3% in weight of nickel. So after this introduction, we would say that the main objective of this project, of this work, is the colloidal processing of tungsten carbide-based materials through the addition of small quantities of metallic nanoparticles as alternative binders. How did we do that? Well, first, by the preparation of high solid content tungsten carbide nickel suspensions by surface modification and the rheological study. And after that, by the sintering of the processed composites by hot press sintering. And finally, we studied the microstructure and the mechanical properties of the final materials. So the first thing we are going to talk about is the preparation of the high solid content suspensions. So first thing to mention, powders we're going to use all over this work. And as you can appreciate here in the micrograph, we have a micronic tungsten carbide powder, which actually has a not very high specific surface. And also we use 2 different types of nickel. The first one, which is a commercial nickel, that's why we call it C nickel. And the second one would be a nanometric nickel we synthesized in our lab. Here I attached the reference. So actually both of the powders are a micronic a nanometric particle size, but the difference is the size of the nanometric nickel powder is much smaller. And it can also be appreciated, there is a huge difference in the specific surface, which is really big for the case of nanometric nickel. There are also significant differences between the shape of the particles. I don't know if you can see it very well, But here, they are kind of stick-shaped particles in the case of commercial nickel, and in the case of nanometric nickel, the particles are rounded and flat. So after that, first thing we did was carrying out some rheological tests to determine the optimal amount of dispersant we are going to add to our suspensions. So in our case, we decided to use polyethylenamine, or just PEI, which is an organic polyelectrolyte, to stabilize our particles in suspension. So after this test, we decided to add some different amounts of proportions of PEI, and with that amount, as we can appreciate here, there is an optimal amount of PEI, which is 1% in weight. And from that point on, the viscosity of our suspension just shoots up, which is not very desirable for our suspensions preparation. So after that, we decided to ensure this data by some powder surface behavior studies by measure the zeta potential of our particles in suspensions. So we stabilize the value of zeta, when the value of zeta potential just remains, we would say we found the optimal amount of dispersant for our formulations. So in this case, in the case of these two powders, the tungsten carbide powder and commercial nickel powder, we determined again there's a 1% of polyelectrolyte of this PEI we add to our suspensions. But in the case of nanometric nickel, the optimal amount is determined here, where the zeta potential value stabilizes, and it will be a 7% of PEI in weight. So here there's a general scheme of the experimental procedure we carried out in the lab. And as we can appreciate here, after the addition of the dispersant, nickel powders, and finally our base material, tungsten carbide powders, they were milled for an hour, and after that, the processed powder were dried. So they were ready for the next shaping, sintering, and characterization steps. After the milling step, we decided also to carry out some rheological tests, but in this case, to determine the optimal amount of solid content for our suspensions. We did this experiment just for this mixture, with tungsten carbide and commercial nickel, and we did the same for tungsten carbide and nano nickel. And in both cases, we could determine there is a 40% in volume, which would be our optimal solid content. And from that point, again, we see the viscosity of the suspension just increased too much. So from that point, the powders were dried, and here there's an EDX analysis of the processed powder. And here in the mapping analysis, we could appreciate in green, I hope you can see it well, that nickel powders in both samples would be very well dispersed. So after that, we consolidated our structures here by doing a hot press sintering process. So here we have the conditions we applied to sinter our samples, and to determine these conditions, we use the shrinkage criteria of our samples method. So, for example, here we have to have a look to some parameters like T on, which is the temperature at which the shrinkage of the sample starts, and T1, which would be the temperature at which the shrinkage rate is the maximum. So from that point, the slope of that curve would determine the maximum temperature at which the sintering process just takes place. So heating stops in that point, and finally the sintering process would stop when the 100% theoretical shrinkage with desiccation of the sample takes place. So under these criteria, we carried out first a binderless tungsten carbide sintering process, and also we did the same for the mixtures with commercial and nano nickel. So as we can appreciate here, well, it is very difficult here because the graph has been shortened, but in this case, both times and sintering temperatures are both really long and high. And this didn't happen for the cases with the mixture with nickel, especially with nanonickel, whose results shows a clearly improvement because the sintering times are much shorter and the temperature, the sintering temperatures just lower, almost 500 degrees. So in terms of density, we could also appreciate there are huge differences between them, achieving even less than a 90% in the case of binderless tungsten carbide. But in the case, for example, of the use of this nanonickel synthesized from us in our lab, this would be even higher than a 98%, which is very good news, actually. So after that, we decided to carry out a microstructure characterization. So here I show you some polished cross-section surfaces of our samples. And as we could expect it in the case of binderless tungsten carbide, and here maybe we can see it better here in further magnifications. There are huge porosity present all over the microstructure in this case, and this is kind of improving where when nickel is present, especially in this case where porosity is even not noticeable. We can also notice there is a huge difference between the grain size, the mean grain size in these three samples, and they are actually very, very small here in the case of the mixture with the nanometric synthesized nickel. After that, we decided to carry out an XRD study, and we could just notice there is no other detected species but tungsten carbide and nickel materials, which can also mean that there is no intermetallic formation or solid solution in these three samples. And finally, just to finish with the microstructure characterization, we just carried out some EDX mapping analysis to this polished cross-section of our samples. And as you can appreciate, I hope, yeah, it's wasn't here. In both cases, in both mixtures, we can see that nickel is just located on the grain boundaries in both cases, and there is, well, yeah, there are some graphite precipitates here, these agglomerates all over the microstructure. So we just carried out some mechanical property tests. In this case, we used some indentation tests to measure both hardness and toughness for our materials. So with 1 kilogram Vickers indentation, we measured hardness, which just gave some remarkable results. In the case of tungsten carbide, we had a very low value of hardness, probably due to all this porosity, but it just improves with the addition of nickel, especially for this case, for the case, again, of metallic nanonickel. And in the case of toughness, we did an 10 kilograms indentation tests, and the results have the same tendency as in the case of hardness. So I would say that the main conclusion of this work is that the addition of small amounts of metallic nickel is proved to be a successful binder, decreasing sintering times and temperature, as well as increasing the density of the final sinter material. Tungsten carbide-based suspensions with high solid contents are colloidally processed, with the addition of just a 3% in weight of nickel of two different types, a commercial nickel and a nanometric nickel synthesized in our lab, but also the binderless tungsten carbide material as a reference. Rheology just revealed that the optimum amount of dispersant was 1% in weight, and solid content for both our suspensions were 40% in volume content, sorry, for the preparation of our slurries, and they achieved a greatly homogeneous dispersion of both types of nickel. By hot press sintering, the density of the final sinter samples reaches to more than 95% for the mixture with commercial nickel, and even more than 98% for the mixture with nanometric nickel. In the microstructure analysis, metallic nickel is located, as we just appreciated on the micrographs, all over the grain boundaries, while some residual carbon just precipitates under sintering conditions all over their microstructures. And finally, both hardness and toughness values of nickel-doped materials are actually comparable to the ones reported in the literature, but the best results were again obtained for tungsten carbide nanonickel. That was all. Thank you so much for your attention. Thank you also to the Spanish government, to the community of Madrid, and also to the JEX Trust for the financial support. If you have any question, I'll be glad to answer them. Thank you again.